Hello everyone, today let's take a look at QP138, just deriving the mean and variance of the uniform distribution. So first of all, in part A, we have x distributed as basically a uniform random variable between 0 and 1, and we just need to find the expected value of x and the variance of x. So let's start with the expected value. So for the uniform distribution, all that means is that basically x can take values with equal probability between 0 and 1. It's obviously a continuous distribution, so we can basically plot it out. If this is x on my x-axis, then I have basically my density on my y-axis. In our case, x is a uniform between 0 and 1, so we have values basically going from 0 to 1, and they're all equally likely, so we're basically just going to have a constant function for our density, right? And it's a straight line because, well, we have a uniform distribution, right? So if x is equal to 1/5, I have the exact same probability density as if x was equal to 1, as if x was equal to any number, right? That's why we have a straight line. Now, this is a continuous random variable, right? So x can take values basically anywhere between 0 and 1. They could take like 0.00006, 0.0007, right? They can take any value within this. Because this is a probability distribution, obviously, when we sum up all the probabilities of x taking each value between 0 and 1, right? That sum has to be equal to 1. So now how do we make sure that the sum of all these probabilities is equal to 1? Well, x is a continuous random variable. It takes values between 0 and 1. So because it's continuous, we basically integrate between 0 and 1 the probability of x occurring. So this right here is our probability density function, right? It's just a constant because we have a uniform distribution. So taking the integral of that, right, it represents our probability between 0 and 1 is just the same thing basically as finding the area under this curve right here. So this is just a rectangle right here. No need to take an integral. We can just find the area of this rectangle. We need it to be equal to 1. So what's going to do that? Well, a height of 1, right? If we have a width of 1, we need a height of 1 to have an area of 1. Obviously, it's just going to be a square. So therefore, our density function in this case, f of x, is just going to be equal to 1, right? That is just this constant function right here, this line, right? It just has a value of 1. So now I know the density function, I just need to calculate the expected value of x. How do I do that? Well, I sum up over all the possible values that x can take, basically the probability of that value occurring. That's just the definition of expected value. In the continuous case, that just means integrating over all the possible values that x can take. So in our case, between 0 and 1 of x times the probability of x occurring, or our density in this case, right, with respect to x. So our density in this case was 1, so we can just do like this. And this integral is going to be super easy. It's just going to be x squared divided by 2, evaluated from 1 to 0. When we plug in 1, we get 1/2. When we plug in 0, we get 0, obviously. So just 1/2, right? That is our final answer for the expected value. And that makes sense because it's going to be right in the middle of our two bounds for x, right? Okay, so now for the variance of x, we've already shown that this is equal to basically the expected value of x squared. So the second moment of x minus basically the expected value of x all squared, like this. We've already calculated the expected value of x. That's just going to be equal to 1/2 squared. So that's going to be 1/4 right here. And now for the second moment of x, the expected value of x squared, we can do a very similar thing. We're just going to integrate over all the possible values that x can take of x squared times the probability of that x occurring, or the density. In our case, that's going to be 1 with respect to x. So when we integrate x squared, we're just going to get x cubed divided by 3, and it's going to be evaluated from 1 to 0. So that's just going to be equal to 1/3. So the second moment of x is going to be 1/3. So our variance is going to be 1/3 minus 1/4, which is just equal to 1/12. So that is the answer for the variance of x. Okay, so now in part B, we are having y be a uniform random variable basically between, instead of 0 and 1, it's going to be between a and b, where a and b are arbitrary. Obviously, a has to be less than b. So what's my probability density function going to look like? Well, let's just graph some stuff. Basically, this is x right here. I know it takes values between a and b. Again, uniform implies that every single value between a and b is going to have the same probability. So we just have this density, this constant function right here, just looks like a line above them. So again, because we know the shape of this density function, it's just a constant, and we have a probability distribution here. We know that when we sum up the probabilities of x occurring for all the possible values that it can take, it must be equal to 1. And because this is continuous, to sum up all these probabilities, we just have to integrate between a and b the probability of x taking that value. And the integral between a and b of this function is the same thing as just finding the area under the curve. And in our case, the area is super easy to calculate because we just have a constant up here. So it's going to have a height of basically the value of our density function, and it's going to have a width of b minus a. So we know that b minus a times the value of our density function, which I'll call f of x, we know that that is going to have to be equal to 1 in order for this to be a valid probability distribution. So therefore, the density function, when we just rearrange this, is just going to be equal to 1 divided by b minus a. Oops, just realized I guess I should have been saying y here, but basically it doesn't matter. Let's just say it's x instead. But now that I know the density, I can just calculate the expected value of x by basically integrating over all the possible values that x can take, again, because it's continuous. So from a to b of basically x times my density is just 1 over b minus a, and I'm integrating with respect to x. And then this integral is just going to basically be equal to x squared on 2 times b minus a evaluated from b to a. So this right here is just going to be equal to, when we plug in b and a, it's going to be b squared minus a squared divided by 2 times b minus a. B squared minus a squared, I can factor that as b minus a times b plus a, and then we're going to have that over 2 times b minus a. So these are going to cancel right here, and we're just going to be left with b plus a divided by 2, which again makes a lot of sense because it is right in the middle of b and a, the two bounds that x can take. Okay, so for a general uniform between a and b, this is going to be our expected value. Now let's calculate the variance. I'm going to have to move to a new page. Okay, so for the variance of x, again, it's just going to be equal to the expected value of x squared, the second moment of x, minus the expected value of x all squared. The expected value of x was b plus a divided by 2, so we can just plug that in right here, and we get b plus a on 4, and let's square the top as well. So for the second moment of x, we can calculate that in pretty much the exact same way. We're going to integrate from a to b, the possible values that x can take of x squared times the density, which is going to be 1 on b minus a with respect to x. And this is just going to be equal to x cubed on 3 times b minus a evaluated from b to a, which is just going to be equal to b cubed minus a cubed on 3 times b minus a. Now let's just do some algebra to simplify this. First of all, you can kind of guess that b minus a will be factored out of this term, right? And when we do some polynomial long division, let's do that. We're going to divide b cubed minus a cubed by b minus a. So b goes into b cubed b squared times, when we multiply this by b squared, we get basically b cubed minus a times b squared. And we're subtracting this off right here, so we distribute that. We get negative b cubed plus ab squared, and then when we add these up, we get 0, obviously, and then we get ab squared minus a cubed. This is our remainder, and now b goes into ab squared, ab times, right? So when I multiply ab times this right here, what do I get? I get ab squared minus a squared b. And I'm subtracting this off, so when I subtract this off, I get a negative here and a positive here, so these are going to cancel, and we're going to get a squared b minus a cubed as a remainder. Now b goes into this term right here, it goes in a squared times, so we say a squared, and then when I multiply a squared by this, I'm going to basically get a squared b and then a minus a cubed, and I need to subtract this, so minus and a plus, and then these are going to cancel right here, so remainder is 0. So we can decompose b cubed minus a cubed into this times this. When I plug that up in here, this is what I get, and then the b minus a is going to cancel, one on top and one on bottom, and I'm just going to be left with this. So this right here is the second moment of x, but to calculate the variance, we still need to subtract off this term right here, so let's do that over here. Okay, now I can just do a little bit more simplifying. This is going to expand to basically b squared plus 2ab plus a squared. I can get the common denominator by multiplying this side by 3, so I get a 12 on the bottom, and then this side by 4, so I get 12 on the bottom and multiply this by 4. Then I'm going to get this term right here, and I just distribute this 4 inside of here and this 3 inside of here, this negative 3, and then combine them over our common denominator of 12. Now 4b squared minus 3b squared is b squared. We have a negative 2ab when we combine this one, and then what else do we have? We have a 4a squared minus 3a squared, so we're going to have plus a squared. That is going to be over 12, and then we can factor the top part. It's just going to basically be b minus a squared divided by 12, and that's pretty much as far as we can simplify it. That's going to be our variance. So this is my variance of x. When x is a uniform random variable taking values between a and b, it's going to be the square difference between our bounds divided by 12. So yeah, this is the simplest continuous distribution, and there's a lot of cool things that you can do with it. So yeah.